Nuclear fission. Nuclear fission is the splitting of larger nuclei into smaller nuclei. Alpha decay is an example of a natural nuclear fission. Nuclear fission can be induced in some isotopes by adding an extra neutron. Nuclear reactors use uranium-235, which is natural, or plutonium-239, which is a man-made isotope. A colliding neutron can be absorbed by the nucleus of uranium or plutonium if it's travelling slowly enough. For example, the following can take place. Uranium-235 absorbs a neutron to become uranium-236. This then immediately splits into lanthanum-146 and bromine-87, and also releases 3 free neutrons. I can demonstrate that with a diagram. Here we have the neutron and the uranium-235. When the neutron is absorbed, it produces uranium-236. This then splits into a lanthanum-146 and a bromine-87 plus 3 free neutrons. This process releases energy, as is shown on the binding energy video. If there is sufficient uranium-235 nuclei available, this splitting can lead to a chain reaction. Here the neutron is absorbed by a uranium-235. When this splits, it releases 3 further neutrons. These could lead to further fissions, releasing more neutrons, leading to further fissions, and so on. Another fission that can take place is this one. Here uranium-235 absorbs a neutron becoming uranium-236 as before, but this time it splits into barium-141 and krypton-92, again releasing 3 neutrons. To find the energy released, we need to know the binding energy per nucleon of the products involved. So here we have the uranium-235 at 7.6 megaelectron volts per nucleon, barium 8.4 and krypton 8.6. So the total binding energy after the fission is the 141 nucleons in the barium multiplied by 8.4 MeVs for each, plus the 92 nucleons in the krypton multiplied by their 8.6 MeVs each, gives 1975.6 megaelectron volts of binding energy after the fission. The binding energy before the fission is the 235 nucleons in the uranium multiplied by their binding energy of 7.6 MeVs, giving a total before of 1786.0 MeVs. The increase in binding energy is given by the final minus the initial, giving an increase of 189.6 megaelectron volts. So the energy released is 190 MeVs to 2 significant figures. Alternatively, we can consider the masses involved. So here's the fission again, and the masses of the particles involved in atomic mass units. So the mass difference is equal to the mass at the start, which is the mass of the uranium plus the neutron, minus the mass at the end, the mass of the barium, the krypton, and the 3 neutrons. This is a mass difference of 0.20 atomic mass units. To get this into kilograms, we multiply by the value of the atomic mass unit, 1.661 times 10 to the minus 27 kilograms, given on the datasheet, giving 3.32 times 10 to the minus 28 kilograms. To convert this to joules, we use energy is mc squared, putting in the values with the speed of light given on the datasheet, gives 2.99 times 10 to the minus 11 joules. To compare this to our previous answer, let's quote it in electron volts, which we do by dividing by the charge on the electron. And this gives 1.87 times 10 to the 8 electron volts, which is 190 megaelectron volts, the same answer as we got before. To find the energy released from the fission of 1 kilogram of uranium-235, well, we know there are 2.99 times 10 to the minus 11 joules released by every individual fission, and we know that 235 grams of uranium-235 is 1 mole, which is 6.02 times 10 to the 23 individual nuclei. So 1 kilogram is 1,000 grams, and each gram contains a 235th of a mole. So in a kilogram we've got 2.56 times 10 to the 24 nuclei, each of which can release this energy. So the energy released is given by the energy per fission multiplied by the number of nuclei that can fission, which is 7.6 times 10 to the 13 joules of energy. This is a huge amount of energy compared to the 2.4 times 10 to the 7 joules of energy released by burning 1 kilogram of coal. It's about 3 million times as much.